Hello, my name is Alejandra Pasillas. In this presentation, I'll summarize my analysis of artificial blood vessels, where I simulated blood flow and structural stress inside prosthetic aorta segments, and I'll walk you through the design of the flow simulation and the structural analysis and the results that I got from that in my final material recommendation for manufacturing. So the objective of the assignment was to understand how blood behaves inside prosthetic blood vessels and how different materials respond to internal pressure. In my case, I chose the aorta, and I used the computational fluid dynamics or the flow simulation to get the pressure. And then I used that pressure to run the structure analysis or finite element analysis to get the strain, stress, and displacement, which is just a number for how much a material deforms or stressed under a certain load. In this case, the load was the pressure, and this led me to make a decision on which material to use, since this methods determine whether a graft is safe, durable, and manufacturable. The three materials I decided to use for this assignment were PT, TPU, and silicone rubber. So for my model, I use actual anatomical dimensions from clinical aorta measurements. I use a 28 millimeter inner diameter with a 1.5 millimeter wall thickness, which gives us a 31 millimeter outer diameter. I created three different lengths, which was 1 millimeter, 10 millimeters, and 100 millimeters long, to see whether geometry affects internal pressure or not. And this also helps verify that longer grafts don't actually accumulate unexpected pressure. For the flow simulation, I use realistic blood properties to create my own fluid in SolidWorks in a physiologic inlet flow rate of 80 milliliters per second, or the conversion to it to meters cubed, which represents peak systolic flow. I also ran the simulation in this case of 5 times of that flow to simulate high demand or like emergency conditions, and this gave me a worst case pressure value that I later used in the structure analysis. So for my flow simulation results, the 1 millimeter tube had the highest pressure gradient because the flow hasn't developed yet and it immediately hits the wall. And the 10 millimeter and 100 millimeter models behave similarly with almost uniform pressure. Pressure also scaled linearly with flow rate, confirming laminar flow. From these tests, the maximum pressure was about 93 Pascal, which I applied in the structure analysis study. For the structural analysis, I used the 100 millimeter tube because it was the most stable geometry for meshing and constraints, and I applied the worst case pressure of 93 Pascal to each material separately. One end of the tube was fixed to represent surgical anchoring. And in this image, I'm showing the 1 millimeter tube instead of the 100 millimeter tube, just because I wanted to show the arrows pointing to the outside of the inner wall. That's where the pressure load was applied. And in the 10 millimeter and the 100 millimeter models, SolidWorks was not showing the arrows, or it was just not as clear as in this image. That's why I chose to use this one as an example. So for the three materials performances, all stresses were under 1 kilopascal, meaning none of the materials were anywhere near yielding point. PT is the stiffest and barely moves. TPU was a little bit more flexible but still has a massive safety factor. And silicone rubber deforms the most, which is not ideal for high pressure arteries. The safety factors help us evaluate how long the durability is. And here all three materials exceed the required strength, but there's more to analyze than just thinking all of them work. Based on the results, I recommend PT for aortic graft manufacturing because it has a high stiffness, which maintains vessel shape under high pressure, and it's already widely used clinically. TPU is more compliant and could be ideal for next generation flexible grafts. Silicone rubber is better suited for low pressure vessels because of its higher deformation. Uh, so my recommendation would be as the highest priority PT, then TPU as a secondary option, and silicone as the lowest option. Here's a material comparison table. As you can see, PT has the lowest deformation and the highest safety factor, which makes it the best solution for this scenario for aortic grafts. But TPU could also work for mid-pressure or flexible grafts, and silicone could work for low-pressure vessels. In conclusion, the results of the flow simulation and structural analysis showed that the graft length doesn't significantly impact the pressure, and that all three materials were structurally safe, while TPU offers a good flexible alternative for graft, and silicone rubber offers a good option for limited to low pressure vessels. PET clearly offers the best strength and stability for aortic grafts, so in this scenario, it is optimal for manufacturing and would be the best recommendation I can give. And I really thank you for your attention.